here. Another example from section 5.6. This one, we're going to plot trajectories. We're going to plot some trajectories of a dynamical system. Okay, so let me give you a moment to copy this down, and then we'll work through the problem. Okay, so here we have a matrix A, and we want to plot some trajectories of the dynamical system. Okay, so what's the first thing we have to find? Here, what's the first thing we have to find? Well, what do we need to find in order to do this problem? Eigenvalues, and good, Binyam, good, Solomon, good, Sega. We need eigenvalues, and we need, that's right, Binyam, eigenvectors. So easy enough to do. Okay, you know how to find eigenvalues and eigenvectors. Okay, you could use MATLAB. And turns out that these are your eigenvalues and eigenvectors. Lambda 1 equals 0.80, and there's an eigenvector of 1, 0 that goes with that. And lambda 2 equals 0.64, there's an eigenvector of 0, 1 that goes with that. Okay. Now, you know, MATLAB, well, yeah, that's fine, that's fine. So then, xk is, let me see, those are semicolons. These are semicolons here. So this problem has real eigenvalues and, of course, then real eigenvectors. Okay. So then the x sub k will equal this expression here. Okay. But to plot the trajectories accurately, we need to well, we need to basically analyze our expression for x sub k. And first of all, as k goes to infinity, what would, based on these eigenvalues of 0.80 and 0.64, okay, what does this x sub k approach? Good, everybody. It approaches the zero vector. Okay, it approaches the zero vector. But when we draw the trajectories, we have to ask ourselves what makes sense and how the trajectories approach the zero vector. So, like, the trajectory would be like, you start at x sub 0, and then you go x sub 1, x sub 2, x sub 3, x sub 4, x sub k. As k gets large, the x sub k's approach the origin. But how do they approach the origin? That's important. I mean, the origin is what's called an attractor, and they approach it asymptotically. They do. And by the way, you can have, based on your eigenvalues, you can have, for instance, a saddle point, or the origin can be a saddle point. The origin can also be a repeller. And you'll do a little studying on that to see that. If you look at the examples in the book, you'll see that. But let's focus on this. It's based on the eigenvalues you have. These eigenvalues, both of them are less than 1. So as k gets large, the x sub k approaches the origin. But this second part here, right here, as k goes to infinity, this part goes to 0 more quickly than the other part, than the first part. Why is that? Why does this part of x sub k go to 0 more quickly? That's right, Binyam. 0.64, that eigenvalue 0.64 is less than the eigenvalue 0.80. So this part of x sub k will evaporate, disappear more quickly. And that then tells you what the trajectories ideally would look like. Okay, that would tell you ideally what the trajectories would look like. So the direction of greatest attraction is the line through the origin, the zero vector, and the eigenvector v2. Okay, that's your direction of greatest attraction. So if you notice here, and this figure I got from the book, it goes with let me see, section 5.6. It goes with the example 2. So let me just see here if I can. All right, I'm letting you look at it for a moment. I'm just want to make sure I'm. So I want to say this kind of in a very fundamental way. You have two parts of x sub k here. The first part with eigenvalue 0.80 and the second part with eigenvalue 0.64. As k gets large, both of these parts of the x sub k approach the 0, 0 vector. They pull x sub k into the origin. But the second part pulls it more to the origin, the part with 0.64, that part of x sub k pulls it to the origin more than the first part of x sub k does with the 0.80. Okay, so that's why the direction of greatest attraction is the line through the origin and the eigenvector v2. Okay, that's why it's the line of that's why it's the direction of greatest attraction. Just see here if I can. The way I like to think about it is, I'll tell you how I like to think about it. So if you look at like this path here, okay, asymptotically as k goes to infinity, the x sub k, you know, as k increases, x goes into the origin. But when it goes into the origin, does it appear to be tangent to the x1 axis or the x2 axis? Any of these solutions, if you look at how they approach, your approach is into the origin, as you get close to the origin, the solutions appear to be tangent to the x1 axis or the x2 axis. And let me see, there's some responses. The x1 axis. And the reason that is because when k is large, this part is gone for x sub k. Right? That part goes away more quickly, leaving you with the first part. Okay, for x sub k. And that's just a multiple of the vector 1, 0. Well, 1, 0 is 1, 0, a vector v1. Is that eigenvector on the x1 axis or the x2 axis? It is on the x1 axis. And so that's why when the x sub k's, as k increases, the x goes into the origin, but it eventually is going to follow the x1 axis by virtue of the fact that that's the part of the solution that's left as k is large. Does that make sense? Does that make sense? You have to stop me if you're uncomfortable. Are there any questions on that? Okay. Matthew's good. Sega's good. So you have to be kind of careful with these kind of problems, because usually these kind of problems, when they talk about the direction of greatest attraction or anything like that, it's usually a multiple choice part. So you have to, you know, just be a little bit careful. But all right, well, let me stop the recording there on